Welcome to this demonstration video for Big Media Intelligence Super Project, and thanks for your valuable time to watch this video. My name is Chenxi and my research topic is urban passenger flow prediction. This part is to introduce the project background. Traffic issues has become increasingly problematic since 1950s. It has a significant impact on human being society, including economy and environment. Over the past 2 decades, the development of intelligent transportation system has an extraordinary impact on traffic efficiency. Passenger flow prediction plays an important role in ITS, including traffic congestion and carbon dioxide emission. Recently, researchers have investigated a variety of reliable theories for traffic flow prediction, and the existing methods could be divided into parametric models and deep learning models. The parametric model refers to a particular model class with a fixed structure. Its parameters represent all the information which is determined by empirical data. ARIMA is a model commonly used by researchers due to its precise simplicity and interpretable outcomes. In the 1970s, ARIMA was implemented to forecast traffic flow using Box-Jenkins method. On the other hand, common filter is a type of model capable of interpreting flow changes. The previous study had proved its superior performance in traffic flow prediction and online learning applications. However, due to the nature of nonlinear and stochastic in traffic flow, parametric models have insufficient ability to cope with data reliably. Due to the improvement of computing capacity for computers, researchers have proposed many deep learning models applied. In the 1980s, RNN was invented to process very long sequences. Even though it can capture sequential data, it does not handle long-term dependencies well as gradient vanishing and exploding. Then researchers proposed LSTM to overcome these problems. The forget gate in the LSTM cell is a subtle controller to regulate the input values. Therefore, the LSTM model has an outstanding performance in long-term sequence. However, the training process of both models is considerably time-consuming due to its complex structure. To optimize the training process, the researchers proposed gated recurrent unit to do machine translation due to its simple structure. This part is to describe the project overview and main contributions. This project is to serve users without an academic background. To improve the accessibility and usability, the finalized project is in the form of a web-based application. The front end of the application is in form of traffic dashboard, and the back end is supported by Python and Flask Web Framework. As for the prediction algorithm, I have proposed an enhanced multivariate LSTM model which takes the public events into account. The experiment applies multiple control groups such as RNN and GRU. As a result, the multivariate LSTM model has achieved the best outcomes. Additionally, the algorithm in the web-based application is to make predictions for future time steps. For visualization, the passenger flow could be visualized by setting multiple constraints such as ID, time interval, and so on. The dashboard also provides users with travel advice by top busy routes and heat maps. Next, I will briefly describe the architecture of the project. As mentioned before, the project is supported by Flask Web Framework, which uses model template view as a pattern. Compared with Django, Flask is a lightweight one and it is easy to pick up. Furthermore, Flask has compatibility with Python libraries such as PyTorch. These are the main reasons for choosing Flask as a web framework. The structure of the project could be separated into 4 parts, as shown in the set map in the slides. Each part represents an independent web page containing different functions. The file uploading page is the index page, and it is the entrance to other functions by preprocessing the dataset. After data preprocessing, users could perform the rest of functions in other 3 pages. Next, I will demonstrate how this system works. In this part, I will illustrate the prediction algorithm. Traffic flow forecasting is essentially a time series prediction problem. It is effective to frame it as supervised learning problem so that we can map input X to output Y. The sliding window method is to reconstruct time series as supervised learning problem. We can do this by using previous time step as input and use the next step as the output as shown in the figure. The sliding window method is feasible for both univariate and multivariate time series. Before we determine the algorithm, we have to observe the dataset. The dataset used in the project is public traffic data from the Queensland government. The two figures describe the passenger flow for the same bus stop showing the different patterns. In the first figure, we could see there is continuous decrease in April, which is different from the second one. This is due to the Easter holiday. Based on the sufficient observations, we conclude that a public event is a significant factor for passenger flow. Since RNN struggles to overcome gradient vanishing and exploding, we choose the LSTM model as the prediction algorithm to handle long dependencies. The multivariate LSTM is the best choice because it supports many-to-one prediction mode. Therefore, this model can deal with multi-dimensional inputs including passenger flow numbers and public event labels. Many machine learning algorithms cannot operate on labeled data directly. They require all input and output variables to be numeric. As the public event data is categorical data, the biggest challenge is how to convert them to numerical data. Here, we use one-hot encoding to deal with public event labels and transfer them to multiple binary integers. For time series generation, we have to define the legs and then use the passenger number as the next time step as the output. To test the effectiveness of the algorithm, we select TransLink dataset ranging from April 1st to April 30th, which is a period that contains the most holidays, such as Good Friday and Easter holiday. The research entity is UK stop, and the passenger flow is aggregated to 15 minutes time interval. As mentioned before, the input size of the model is 2, and the rest of hyperparameters are shown in the slide. Now, I would like to conduct an ablation study to testify the event label for multivariate LSTM. In the study, the conventional LSTM has no event label. The outcome suggests that the multivariate has a better MAP and RMC than the conventional one. This has proved the effectiveness of the event label. In the experiment, we had to validate the multivariate LSTM by comparing it with control groups. It includes 3 deep learning models and 2 parametric models. Please note the deep learning models in control groups have the same hyperparameters as multivariate LSTM with single flow input. As shown in the table, the multivariate LSTM has achieved the best performance in both MAP and IMC. To better understand the model, I would like to analyze the parameter sensitivity. Here, the analyzed hyperparameters include different time steps and learning rates, and the outcome is shown in the slide. Based on the outcome, the long time steps do not guarantee the prediction accuracy. This may be due to the signal pattern of the passenger flow. Then there is no obvious difference in learning rates. The reason is the model has already converged after training. Now, I will demonstrate how the prediction algorithm works in the application. In this part, I will illustrate the visualization function. Before visualizing pattern flow, we have to consider how to preprocess it. Here, the record with the missing string value has been dropped, such as the lighting time. Then we fill the missing values of pattern number with its median value. After data preprocessing, we generate pattern flow by the aggregate function. Next, we can set constraints on the pattern flow. The constraints include entities, time interval, date, and timing. In the panel, users can view statistics and use zoom in and zoom out function. Finally, the function top-busy-root provides an overview of pattern flow so that users can check daily and monthly pattern flow for each route. Then, users can use a heat map to check the pattern flow distribution by geographic location. They can use a slide bar to conveniently change the date. Now, I will demonstrate how the visualization function works in the application.